Good day, everyone. Warm greetings from South Africa. My name is Manel Maton, and we are very disappointed that we cannot come to Spain for this conference, but we are still grateful that we can share our work with you on this platform. So the title of our study is Scientific Discourse, and it's about our first year students and whether they can express themselves in science. I'm a lecturer in the Faculty of Science at Stellenbosch University, and more specifically in life science, or biology as we call it. So this brings me to scientific discourse, basically the language that we as scientists use. So like many other disciplinary languages, scientific discourse is a specialized language which is semantically very dense and practically foreign to novices in the field, which for most includes our students. Now, in contrast, our science classrooms often look very different. And in these spaces, often very little of the skill of genuine scientific discourse is modeled or even fostered. And instead, these learning spaces seem to be more lecturing orientated and in reality, therefore, preventing argumentation or even regular conversations among the students and with the lecturer. Many scholars therefore argue or ask that educators need to deliberately model scientific discourse and create opportunities to practice this new language of science. Marshall and Case reasons that in not allowing space for critical engagement with the values and the ways of thinking, many students are implicitly excluded from successful engagement with the subject. What we also have to consider is that writing scientifically can be a challenge for many students, even for those students writing in their home language, which in the South African context is often not the case. Interestingly, students often require more skills to communicate their scientific thinking in a written form than to communicate it verbally. And this is due to a higher level of language skill that is needed for writing than for speaking. It is thus evident that language proficiency is a significant factor, especially for first-year students. And to address these concerns, many institutions of higher education have implemented academic literacy courses, with the add-on language courses being the most dominant format. However, many studies showed that academic literacy is taught more effectively when it is combined with disciplinary content. So this brings me to the aim of this study and the specific problem that we are looking at. And I will explain it using this type of graph. Here we have an x-axis and a y-axis, and towards the bottom of the y-axis we have simpler meaning, and towards the top more complex meaning. So when we look at scientific discourse in a written form, it is rather complex in meaning, and this is what our students need to deal with. They first need to read the type of scientific discourse as it is found in all the sources, for instance a first year textbook. And thereafter we expect them to make sense of this meaning and then to formulate it and to write it in their own understanding. And we find that this is where the problems arise. So our aim was therefore to explore ways to assist our students in developing their scientific discourse, using collaborative pedagogy as well as project-based learning. Now, the collaborative pedagogy was a collaboration between us, the disciplinary lecturers, as well as our colleagues, the academic literacy lecturers, and we would have a combined project where students would have an opportunity first to develop their scientific language skills. After that, we would look at their scientific discourse as they wrote it in their summative assessments following the project. But just as a baseline, we also looked at the corresponding discourse from the first year textbook as well as the school textbook. Now, in this study, we used Legitimation Code Theory as our conceptual framework. It is also known as LCT. LCT is a practical framework that is being used to explore a host of issues, practices, and contexts in education and also beyond. Now, the LCT dimension of semantics constructs social fields of practice as semantic structures, whose organizing principles are conceptualized as semantic codes. So to explain this in simpler terms, this is the so-called semantic plane. On the y-axis here we have semantic gravity, which is now the degree to which the meaning relates to context. So if the meaning is very context related, so for instance related to real world context, it is stronger in semantic gravity, and if it's more abstract the meaning, it is weaker in semantic gravity. Similarly, on the x-axis here, we have semantic density. So if the meaning is simpler, it would be weaker in semantic density, and if the meaning is more complex, it would be stronger in semantic density. Now, in this study, we only made use of the concept of semantic density, which is the degree of complexity of meaning. So to go back to my previous graph where I showed you the simpler meaning towards the bottom and the more complex meaning towards the top, we can now infer the semantics dimension of LCT, which means that down here we would have weaker semantic density and towards the top stronger semantic density. So again, when we're looking at scientific discourse, the reading that the students need to do from their first year textbook, for instance, we're talking about quite complex meaning. On the other side, what we expect from them in summative assessments is also scientific writing that is complex in meaning. But students have a problem with this, and often to cross this gap between reading the complex meaning and then producing scientific writing that is also complex in meaning. So Legitimation Code Theory found a way to actually connect these two. They call the very complex meaning high stakes reading, and they call this writing high stakes writing. So in order to then basically fill the gap, they call this type of graph where we have this wave, it is known as a semantic wave. So it literally means that the complex meaning needs to be unpacked into simpler meaning before being repacked into more complex meaning. And this is exactly where our project came in, to provide students with an opportunity to unpack this complex meaning and to thereafter repack it in their own words into more complex meaning. So this provided them with an opportunity to develop their scientific discourse before having to write a summative assessment. So how did we analyze the data? As I've explained before, we used the summative assessments of these 6 students. We selected 2 questions or 2 topics that the students had to write about. So these would be at least 10-mark questions and more. And as I've said, as a baseline, we also included the corresponding content from the first year textbook as well as the school textbook. So how did we analyze the discourse of the students? As I've said before, we used the semantics dimension of LCT and specifically the concept of semantic density. Later on, Mayton and Doran proposed an even finer translation device for the analysis of discourse. So if we look at scientific discourse, we can distinguish between technical words and everyday words. When we look at technical words, we can further distinguish between conglomerate words and compact words. And these are 2 of the examples coming from the student's text. Here we can see nucleoplasm has 2 distinct parts, each with a technical meaning, whereas nucleus is just a single part with a technical meaning. When we look at everyday words, we can again distinguish between 2 groups, the so-called consolidated words and the common words. And here we have 2 examples of these. And then between consolidated and common words, again, we can distinguish between even more categories. So basically, every single word of the students could be placed into one of these categories, ranging from very complex meaning to very simple meaning. So what did we find? Our first finding was that the scientific language that are used in the school and the first year textbooks differ significantly. So one would think that this is expected, but it was more than what would be expected. And this was in terms of the volume, but also in terms of the complexity. So this graph here shows you the very significant difference between the school textbook as well as the first year textbook. On the side here, we can see the categories going from simpler meaning towards more complex meaning. And the red and the orange bars are the most complex words that the students can use. And one can see that those two categories are completely absent from the school textbook. Also, what the semantics dimension of LCT considers is how these words relate to one another and together. We therefore constructed a so-called concept map. This was for the nucleus of the eukaryotic cell, and one can see these different circles represent the different terms or the words and how they relate to one another. So these are the words that the first year textbook uses, and then showing their relatedness. If we compare this to the school textbook, one can see that the school textbook only used 4 of these terms, and also it didn't really show how they relate to one another. Our second finding was that the scientific vocabulary of the students varied considerably. Now one has to take into account this is now after the project, wherein the students had time to develop their scientific discourse skills, but also to come to terms with all these different terms that are being used and the complexity of these terms. So in this graph, again, one can see the simpler meaning towards the bottom and the complex meaning towards the top. So if one takes a look at student 4 and 5, one can see that these students had many words that they used, and many of these words were in the more complex categories, whereas students 1, 2, and 3 really battled to express themselves still. Going back to that concept map that I showed before that we constructed from the first year textbook, this is student 4, and one can see that she used nearly all of the terms that was used by the first year textbook except for the one, and she also could explain it in the way that showed relatedness of these terms. If we compare that to the other students, we can see that student 5 also used most of these terms, and he showed very good understanding of how they relate to one another. But many of the other students they either did not know these words, or they did not know how to use these more complex words and terms. Our third finding was that the scientific language skills of the students varied considerably in terms of the way that they would explain, and this was the way that they were able to unpack the complex meaning. Now this is student 4, and this is how she described the nuclear envelope. Now LCT semantics research showed that successful discourse is characterized by a wave type of profile called semantic waves, and here one can see such a profile. The blue line is student 5, and one can see how her discourse follows this by constantly shifting between simpler meaning and more complex meaning, whereas students 1 and 3 also were able to do a form of semantic waves, and one can see that they probably developed some kind, or they underwent some kind of development through the project that happened before, but they need a lot more opportunity and practice for this type of skill to develop. Our fourth finding was that the explaining of the complex concepts in a textbook is very concise when we compare it to that of the proficient students. So here again, in the blue line, we can see the semantic profile, the semantic waves of student 4 as she explained a specific concept. And in contrast to that, one can see the red line here. So also semantic waves, but a very short line. So these are exactly the same explanations, but the very concise and a very unpacked version of that. And it is a big difference. So to conclude, the first year and the school textbooks vary substantially, and this is with regards to complexity of meaning, but also the volume of meaning, and this creates quite a big gap and a very big jump from school to first year in biology. Secondly, the levels of student proficiency varied significantly regarding their scientific vocabulary and language skills. So even after having an opportunity to practice, there was still a big variation for the students. And by doing this, we realized that our project needed two more components. Firstly, a component where students would have time to talk about these concepts before they needed to write about those concepts, and then just simply more time and effort and opportunities for many of these students. And then lastly, there is a need for science pedagogy that would allow students time and opportunity to develop fundamental skills such as scientific writing, and this will help them a lot to cross that gap between having to read the complex text and then producing some complex scientific writing in the end. We just want to say thank you to our colleagues from the academic literacies and from the Language Center of Stellenbosch University. Thank you for this opportunity.